In this video, we're going to look at solving linear inequalities. So instead of equations, we'll be looking at inequalities. Now, the actual act of solving linear inequalities is very similar to solving linear equations. So we're going to spend most of our time on how to express the solutions, because that is the thing that seems to cause more challenges for students when solving linear inequalities. So we're going to start out with that. So let's start out by just looking at a few different linear inequalities that are already solved down for x. Alright, let's start with these two. X is less than 2, or x is less than or equal to 2. Now with these, I know some students get kind of worried or stressed out about whether that's a less than or greater than sign and just keeping it straight. I like to always encourage students to think about the symbol as it's meant to be thought of. It's not about alligators or anything like that. Basically, the bigger side of the symbol is next to the bigger item. So this is saying that 2 is bigger than x. The smaller side of the symbol is next to the smaller item. So x is smaller than 2. So if you keep that in mind, then it doesn't matter. Sometimes I even say it wrong, but the idea is that one side is smaller than the other side. So if I write this, just for example, like this, that's saying that 2 is greater than x. So that's actually a greater than sign. But what we always care about is the x. So when we see a statement like 2 is greater than x, well, in terms of solutions for x is less than 2, even though it's expressed using a greater than sign. So what's more important than whether it's a greater than or less than is where does x live in relation to the number that it's being related to. So with that notion, there's a few different ways that we like to express where x lives in relation to the number it's being related to. So the first is just the inequality, to say something like x is less than 2. Another is using a graph. And in this case, when we're talking about graphing, we're not talking about what people usually think of, which is two-dimensional graphing. What we're talking about is just one-dimensional graphing on a number line. So if I have a number line and I label a 0, I always like to label 0. And then, 2 is to the right of 0. I'm not really concerned about labeling all the details beyond that. So then when we say that x is less than 2, then we're going to shade on the graph all the places where there is value that would be less than 2. So we'll shade to the left of 2, like so. So that's showing what we're shading is all the values that are less than 2, because that's what x is. Notice I didn't label the graph with an x or anything like that, because x doesn't live like over in one particular place. So I wouldn't say that this is x. That's nonsense. X is all the values in the shaded region that I gave. Now to the right, we also have this other one. Now this one has the equal bar. So this is saying that x is less than 2, but it also can be exactly 2. So x is less than or equal to 2. So when I go to put that on a number line, what I'm going to end up with is something very similar to what I've done with the other one, because x is everything less than 2. But the thing is the one on the left is just less than 2, and the one on the right is less than or equal to 2. And so we have to have something different go on at 2 to distinguish these two. And the notation that was decided on is that if it doesn't equal 2, you're going to use an open circle. If it equals 2, you'll use a solid point. The solid point is saying, hey, I'm shading on that value as well. The open circle, I kind of think of it like a ghost point. When you draw a ghost, let me see if I can draw a ghost here. Little, Pac-Man ghost. You just draw the outline to say, hey, there's nothing there. But you have to draw the outline to say that there's nothing there. Otherwise, it would just be like you're talking about a ghost, and people will think you're crazy because there's nothing there. Or something like that. Anyways, So it's a ghost point. We put a point that to say, hey, there's nothing at 2, and the way we do that is just leaving it open. Alright, so those are some examples on how you would shade with less than. Let's look at a couple others just to make sure we have the shading down. Alright, so let's do one where we say that x is the bigger thing, so x is bigger than 0 or x is greater than 0. Now here I'll put my 0 on the number line, but I don't need to put any other number. I'm going to shade everything bigger than 0, and I'll leave an open circle at 0 because it doesn't have an equal bar. It's going to be open at 0. So that one's very similar, except it's a greater than instead of a less than, so x is on the bigger side of 0. This last one I put up here is a good deal more complicated. These are what we call compound inequalities, and it basically has 2 inequalities in one. I'm going to start by putting my 0 on the number line, a 2, and a 3, because those are the numbers x is being compared to, and I always like putting 0 on the number line. Now when we look at this, basically there's 2 statements here. One statement is saying that x is less than or equal to 3. The other statement is saying that x is bigger than 2. So if you read that from the x side, that's saying that x is bigger than 2, because if 2 is smaller than x, then x is bigger than 2. And what we want is the place where both of these are true. So the place where x is less than 3 and bigger than 2 is the space between those two numbers. And then as far as 2 goes, it is strictly less than 2. It's greater than 2, so we put a ghost point there. And it equals 3, so we're going to put a solid point there. And so, if you just look at that expression, it looks like x is between the 2 and 3, and you can kind of go with that notion. There are places where you can get a contradiction and stuff like that, but we're not going to be working about those cases. So it'll always end up being shaded between those numbers. And again, the reason why it's an open circle at the 2 is because when x is related to 2, it's not equal to it. When x is related to the 3, it does have the equal bar, so we put the solid point. Okay, now that we've seen how to graph it, there's another way that we can express the solution set for x, and that's interval notation. So let's look at that now. When we're expressing intervals, just in everyday language, we usually express the beginning and the end of the interval, and we're going to do the same thing with interval notation for to express a solution set that ranges over a broad range of values, continuous range of values. So basically what we're going to do is express where x values start and where they end. And we're always going to scan from left to right when we do this, because interval notation always needs to be least to greatest. The easiest one of these to start with is actually the compound inequality when it comes to interval notation, just to get a notion of what's going on with it, then we'll kind of work backwards from there. Okay, so with the compound inequality, the interval where we've shaded, it's going to start at 2 and it's going to continue until 3 when expressed from least to greatest. Okay, so you wouldn't do 3 to 2. You're always going to read at least to greatest. Now, what's going on at 2 and what's going on at 3 are two different things, because we want to include the value of 3 but exclude the value of 2, and we need notation to symbolize that. So to exclude the value of 2, we use a parenthesis, and to include the value of 3, we use a bracket. And that's just something you're going to have to do your best to remember. It's just a silly little memory trick, but something I like to say is the equal bar and the straight bracket kind of go hand in hand. So that if that helps you, great. If not, one way or another, you're going to have to find a way to remember it, that if it's a solid point or an equal to, you use the square bracket. If it's an open circle or doesn't have the equal bar, then you're going to use a parenthesis. Alright, so that's what it looks like when there's numbers on both sides. So when there's numbers on both sides, there's a clear beginning point and a clear ending point. Now on this next graph, we're just going to work backwards through these. So the next one, working least to greatest, that I start at 0, but then I go on. This is saying it goes on forever and ever. And the way we represent that is we use an infinity sign. So it's going to start at 0 and it's going to go to infinity. And then as far as parenthesis, at the 0, we need that because there's an open circle. We're also going to use one for infinity. Basically, the parenthesis notation tells us that it does not equal that value. The bracket tells us it does equal that value. And since you can't actually get to infinity, you'll never equal infinity. And so that's why we're using a parenthesis or a parenthesis for infinity. So if you're going all the way out to infinity, parenthesis, it kind of just curves around it, just like the infinity symbol is curving. So infinity will always use parentheses. Okay, now on the next one, working backwards over here, we have it pointing to the left. Now that is also saying it's going to infinity, but in the negative direction. So the way we write that is negative infinity, reading left to right, and it's going to go until 2. So for the infinity, it's always going to be round, and at the 2 it's a solid point, so it's going to be square. Now again, this is always going to be least to greatest, and so a negative infinity will always be on the left, and an infinity will always be on the right, because that's the only way it'll work, least to greatest. So then the last one here, just real quickly, is negative infinity to 2, parenthesis, and then a parenthesis, because it's an open circle at the 2. Interval notation is a very unforgiving notation. There's no leniency at all. You have to use the right parenthesis or square bracket. You have to go left to right, least to greatest. There has to be the comma in the middle. Everything means something with interval notation. So all of the strokes are symbolic in some way. So just be really careful about that and make sure that you're seeing which one means what, because every single thing is significant and there's no leniency. It has to be exactly like what mine look like. There's not any room for creativity on these. Alright, so those are the different ways of expressing possible solutions for inequalities. The first one here, this is called the inequality notation. And this is a line graph. And then the last one was interval notation. So those are 3 different ways of expressing the solution, and you're going to need to be able to do all 3. Now that we know how to do that, let's actually look at solving some linear inequalities. Okay, so here we go. Our directions are to solve, graph the solution, and write an interval notation. And our inequality is 2x plus 3 is greater than or equal to 8. Now the way you solve this, as I've already mentioned, is very similar to how you solve an equation. So we want to get x by itself by undoing what's happening to it on the left there. So I'm going to start by subtracting 3 from both sides. When I do that, I get that 2x is greater than or equal to 5. So just like an equation, except there's a greater than or equal to in there instead of an equal sign. And now to get x by itself, I need to divide both sides by 2. That gives me that x is greater than or equal to 5 halves. So that's my solution. X is greater than or equal to 5 halves. And then I was asked to graph it. So I'm going to draw my number line with a 0. Don't need to worry about like whether what 5 halves is between. You just need to make sure you get it on the correct side of 0. So 5 halves is going to be to the right of 0. And then the greater than tells me to shade to the right of that. And the equal to tells me to put a solid point at the 5 halves. So that's the graph of that. And then interval notation from left to right is going to start with 5 halves. It's going to go to infinity. At the 5 halves, I will have a square bracket. And the infinity will have a round parenthesis. So that's the deal. We solved it, we graphed it, we wrote it in interval notation. So hopefully all of that kind of flowed and made sense to you. We're going to do a couple more examples that are a little more convoluted, but most of the solving process is like equations. There are a couple curveballs, and we'll see those in the next couple of examples. Alright, so here we have the same directions. Our inequality this time is 2x plus 3 is less than 5 times the quantity x minus 4. So this one's going to need a little bit more work to solve it down. So we're going to start by distributing the 5. That gives us a 5x minus 20. Now I have x's on both sides of my less than sign, so I need to get those so they're on the same side. So I'm going to subtract off my 5x on the right. What I do to one side I have to do on the other. That gives me that negative 3x plus 3 is less than negative 20. And so now we're back to kind of where we were at with the start of the previous example. So we're going to subtract 3 from both sides. That gives me that negative 3x is less than negative 20. Now what I need to do is divide both sides by negative 3. And this is where we get one of the curveballs that you have with inequalities. When I divide by the negative 3, what happens is that the inequality symbol flips from being a less than to a greater than, and I get 23 thirds. So what's happening there, the rule is if you multiply or divide both sides of an inequality by a negative, then the inequality flips. So again, if you multiply or divide an inequality by a negative number, then the inequality symbol flips. So what's going on there is when you multiply or divide something by a negative number, you're changing whether it's on the positive side of 0 or on the left side of 0. And the positive side of 0 and the negative side of 0 are mirror opposites of each other, and so it requires it is necessary for it to flip like this. So this is probably the easiest, at least one of the easiest rules of math to forget, even if you know it and understand it. So I just encourage you to put that on kind of your little list you go through when you're finishing up a test to double check if you got it right, because it's just really easy to forget to flip that inequality when necessary. So our solution here is that x are all the values that are bigger than positive 23 thirds, and now we need to graph that. So on the graph, I'm going to put a 0, and then 23 thirds is to the right of 0, and then we're going bigger than that, so we're going to shade to the right of that, and then in this case it's going to be our ghost point because there's no equal par there. And then for our inequality, we go from 23 thirds to infinity with parentheses on both sides. So that is really one of the big curveballs with these inequalities is going to be anytime you multiply or divide by a negative number on both sides of the inequality, it causes the inequality symbol to flip. Now keep in mind, like when we're solving these, we're never really multiplying both sides by a negative. Pretty much this rule, that's a possibility in general, but it's not going to happen for us when we're solving these. So the rule in general comes into play when we're dividing, and we're usually, if you're solving these, just dividing off that last step when you divide the coefficient of x off. So that's when it can happen, but you only flip the symbol if that coefficient of x is a negative when you divide that negative off, not just when you divide. And not just if the result is negative, only if you're dividing by a negative number. So that's the first curveball. Let's look at the next example to see the other kind of weird case with solving inequalities. Alright, so here we have one of the compound inequalities like we did when we were working on graphing and writing interval notation. So it has two inequality symbols all in one relation. So we have 2 is less than or equal to 3x plus 2 is less than 7. Now with this, I want to tell you the type we will be working on. The x is always going to be in the middle piece of these, and you're just going to leave the x there and undo what's happening to it, just like you would if it's an equation. So we're going to subtract 2, we're going to divide by 3. But instead of thinking that we're doing that to both sides, now since we have 3 sections, we're going to do it to all 3 parts. It helps some people to like build walls here, so they remember that there's 3 sections, and whatever they do, they have to do it to all 3 sections. So we're going to subtract 2, but I have to do that all the way on the right and on the left as well. The result of that's going to be 0 is less than or equal to 3x is less than 5. Now, I'm going to divide each section by 3. So I'm going to get 0 is less than or equal to x is less than 5/3. Now notice when one side's zeroed out, I didn't lose that section. If you start with a compound inequality, you're always going to have 3 parts. You're always going to have a compound inequality. If it zeroes out completely, you just put a 0 in there to hold the place of that section. But you're never going to lose one whole section. Alright, so that's how you solve it. You don't really do anything with the x. You're just going to undo what's happening to it. But whatever you undo in that middle section, you're going to have to undo in all 3 sections. So now that we have that, we need to graph it. So here, the numbers we need on the number line are 0 and 5/3. And so x is bigger than 0, and it's less than 5/3. So that means we're going to shade between it. At 5/3 it's not equal to it, so we use a ghost point. And at 0 it does equal it, so we use a solid point. So that's the graph. And then for the interval notation, we have a square bracket with 0 to 5/3 with a parenthesis. That's it. That's our interval notation. So that's how you do it when there's 3 sections or it's a compound inequality. Go ahead and give some of these a try and see how you fare.